Last day, we ended with this, this example where we had a 1 kilogram bar that was 1 meter long, and we had a 1 kilogram mass that was hanging 80 centimeters from one end, from the left end. And we wanted to know how hard those spring scales were pulling up at the left side and the right side. And we worked it in one particular way, and I'm going to work it a different way this time. Now, I'll remind you that we're looking for forces by the spring scales on that bar. And so we're going to draw a free body diagram, indeed an extended free body diagram of that bar. And the first force we put on any free body diagram, be it a regular one or an extended one, is always the weight force. And we always, every stinking time, put it at the center of mass. Now, you're going to be tempted to put it somewhere else later in this lecture. I would encourage you to always put it at the center of mass, okay? Now, there are no magnets in this problem, so I asked, what's touching that bar? Well, I've got that 1 kilogram mass pulling down with a tension force on the string of 10 newtons. I also have the 2 spring scales pulling up with a force that I'll call TL and T right. Now, last day, I chose to put the pivot right here. And I explained that there's only two reasonable places to put the pivot. Now, this bar is not rotating about any point in the universe. And so technically we could choose any point in the universe, a point in Kansas, if you will, and balance the torques about that point. But there are only 2 points that will give us easy math, and that's usually what we want, is easy math. If I choose my pivot to be here, then this force does no torque about that pivot because there's no lever arm, okay? And that means that this unknown force would be eliminated from my equations. Well, that's what I did last time. The other choice that makes sense would be to put the pivot here and eliminate this unknown force of the right spring scale pulling. And that's what I'm going to do this time. I'm going to put the pivot here and show you that I get the same answer either way. Okay? Now, once I have this pivot location identified or chosen, I have to balance all the clockwise torque with all the counterclockwise torque. Now, how do I decide which force is doing a clockwise torque and which force is doing a counterclockwise torque? Well, I have to use my imagination. I imagine that there's a great big golden spike going right through that pivot that's just essentially forcing that beam to rotate about it. Okay, this bar is forced to rotate about this pivot right here as if this were a hinge on a door. And then I ask myself, I say, self, if this were the only force acting on that bar, and it was forced to rotate about that pivot, would this force be trying to make it go counterclockwise or clockwise about that pivot? Well, I think you can see that this force is trying to make it go counterclockwise. This force is also trying to make it go counterclockwise. And this force is trying to make it go clockwise. And this force, as we said before, you know, that's like pushing at the hinge of a door. That's not going to do any rotation whatsoever. The torque due to this force is 0. So when I set up my equation, the only force that's giving me a clockwise torque is this unknown force, the tension in the left spring scale. And I have to multiply that force by its lever arm, meaning the distance to the pivot. Okay? I have 2 torques that are trying to make it go counterclockwise. I have this weight force of 10 newtons times its lever arm, the distance to the pivot. And then I have this force by the this mass pulling down at 10 newtons, and its lever arm is the distance to the pivot, or 0.2 meters. Now when I solve that for the unknown left tension, I get 7 newtons. Now again, the old rules still apply. Newton's second law still applies to the center of mass of this system. And that means all the force down has to balance all the force up if the center of mass has no acceleration. Well, I got 20 newtons down. I gotta have 20 newtons up. And so that means that right spring scale is pulling with a force of 13 newtons. And I hope you saw in the last lecture that when we uncovered the spring scales, that's exactly what we found, was 7 on the left and 13 newtons on the right.